Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello everybody and welcome back to this video series for trigonometry. This video series is actually meant for college algebra students or students in a college algebra course or those who are taking pre-calculus. For those who are taking pre-calculus, you should have already had a full course in trigonometry. However, I find that most students who enter into pre-calculus for the first time in college have not had a full semester course of just trigonometry. So that's what this video series is meant for, really for everybody to learn a full gamut of trigonometry. You should have watched prior to this video my video series on angles. Obviously, with a name like angles, it doesn't sound very awesome, but it covers what an angle is, all the definitions needed to understand angles in trigonometry. It also covered a very important part of angles, which is radian measure. That is critically important for our future conversations in trigonometry. So this video and this video series is going to focus on right triangle trigonometry. Actually, honestly, this video is just going to focus on triangles in general. And then we're going to go through slowly and take a section that out of a textbook might be a single short section or something like that. We're going to expand it into a big, deep conversation. This is for somebody to get a very good background in trigonometry. So that's what we're trying to do here. That's why we're taking our time with it. So let's talk about triangles in general. And all of these terms or phrases that we're going to be using will be used throughout your trigonometry course. So it's good to kind of refamiliarize yourself with them here. So what are acute and obtuse angles? We'll start there first before we talk about triangles. An acute angle has a degree measure of less than 90 degrees, but greater than 0 degrees. So it could be any angle. Remember, we have an angle in standard position if its initial side is on the positive x-axis. And then here we're opening through an angle less than 90 degrees. Let's just say that's 38 degrees or something like that. That would be an acute angle. Strictly less than 90 degrees, but still greater than 0. That would be an acute angle. An obtuse angle has a degree measure greater than 90, but less than 180. So that would be something like this. If this is our initial side right there, and this is our terminal side, so our angle to open this way, that might be 110 degrees, or let's say 117 degrees, just to make it odd for no reason. Then that would be an obtuse angle. By the way, some people will ask, well, what do you call an angle that's greater than 180 degrees? That would be called a reflex angle, which you're not going to see in trigonometry, so don't really worry about that. Well, you'll see them, but you won't see that or hear that wording in your trigonometry course. So really all I concern myself with here is acute angles and obtuse angles. Remember, to be obtuse, it's less than 180 but greater than 90 degrees. And if to be acute, it has to be less than 90 but greater than 0 degrees. And also remember that the radian measure for 90 degrees is pi over 2. And the radian measure for 180 degrees is pi. I'm just going to sneak those in as we can. This theorem should have been proved in your geometry course, that the sum of the interior angles of a triangle is 180 degrees. So just to let you know, that is an assumed prerequisite, but I just like to kind of write that in there. What I mean by interior angles is if you have a triangle like this, which is non-right, doesn't have to be a right triangle, but we'll call this triangle ABC. Okay. So I will denote that triangle ABC, just so I have a notation I can talk about. And this theorem is basically telling us that angle A plus angle B plus angle C must equal 180 degrees. That's all that you have for the interior angles of a triangle. And that should be well known to you at this point, but there you have it. I don't want to waste too much time on that. Now let's really get into types of triangles. There's two major types of triangles. There are acute triangles and obtuse triangles. An acute triangle is a triangle in which all interior angles are acute. And that's why I needed to define what an acute angle was earlier. For example, as you can see from this drawing right here, that's likely an acute triangle. Actually, it is, because all the angles you see here, that angle, this second angle, and this third angle, look to be all less than 90 degrees. And so therefore the triangle is acute. If any of them is 90 degrees or greater, it is no longer an acute triangle. And contrary to what a lot of students think, even though we're in a section called right triangle trigonometry, that should imply to you that trigonometry can apply to other types of triangles, because this specific talk is about right triangle trigonometry, but later on we're going to grow trigonometry to be applicable to acute and obtuse triangles. Speaking of obtuse triangles, a triangle in which one interior angle is obtuse is called an obtuse triangle. Now, this is such an interesting definition only because it says a triangle in which one interior angle. Actually, I should just highlight the one. Well, the question should naturally arise. Why is it only one? Why can't it be two? Now, let's talk about that. First off, this is an obtuse triangle. You have a small angle there, a different small angle there, and then you have a very large angle greater than 90 degrees right here. And that angle greater than 90 degrees is an obtuse angle. Therefore, this is an obtuse triangle. Now, why is it that you cannot have more than one obtuse angle in a triangle? Well, because if you did, you'd have two angles that are greater than 90 degrees in a triangle, and therefore the sum of the angles within the triangle would be greater than 180 degrees. Now, I'm actually going to write that down because I want you to get used to this idea of argument by contradiction. So let's go ahead and just showcase what an argument by contradiction is, because I like to sneak that in as often as possible if I can. So I'll start with the supposition. Suppose we have two obtuse angles in a triangle. Let's go ahead and call these angle A and angle B. Of course, you have another angle in there. By definition, we have the following. Therefore, angle C must equal 180 degrees minus angle A and minus angle B. But angle A and angle B are obtuse, and so they are greater than 90 degrees. Therefore, their sum is greater than 180 degrees. And so, angle C, which is 180 degrees minus, and what I'm going to do is just factor out the negative sign off of this stuff right here, minus the group angle A plus angle B, is going to equal 180 degrees minus some number that's greater than 180. So I'm just to say n, where n is greater than 180. Well, that means that this is a negative number. That's not supposed to look like an angle sign, but this is less than 0. So this tells me, because 180 degrees minus something greater than 180 degrees is negative. So that tells me that angle C is a negative number. And that can't happen within a triangle. This is a contradiction. And therefore, somewhere along the way, an assumption we made must have been wrong. Now, if you look through all of our language, the only time I made an assumption was right at the beginning with this word suppose. And that was that we supposed we had two obtuse angles. Obviously, therefore, we cannot have two obtuse angles. We can only have at max one. Now, I'm not really supposed to be proving that, but the reality is, I think it's good, again, just to see logic kind of formed out for you in that format, I guess. Now we're going to start getting into the actual types or kinds of triangles. We talked about the two broad categories, which are acute triangles and obtuse triangles. Now we're going to start talking about the types themselves. And the most common, or I should say the most beautiful type of triangle, is an equilateral triangle. It's a triangle in which all three sides are of equal length, and that means that all the angles are of equal size. And that theorem just basically says that right there, that each interior angle of an equilateral triangle is 60 degrees. So I'll just showcase that here. There we go. We have a good equilateral triangle right there. And all interior angles are the same. Whoops. You want them all to be 60 degrees. Remember that 60 degrees from radian measure is the same thing as pi over 3 radians. Again, trying to sneak that in as often as possible, and that is because, again, 360 degrees is the same thing as 2 pi radians. So you would just divide both sides by 60, let's just say. If you divide both sides by 60, you get 60 degrees, or sorry, not by 60, but by 6. Divide both sides by 6, you'd get that 60 degrees is equal to 2 pi over 6, which reduces to pi over 3. It's a really nice way of doing that, actually. Another common style of triangle that deserves a name is an isosceles triangle. An isosceles triangle is a triangle in which only two sides have equal length. In other words, that it's not equilateral, not all three sides are the same, but at least two sides, or not at least, exactly two sides have the same length. So something like this would be isosceles. You might recall this from your geometry course, that they note similar length sides with these dashes right here, and then sides that are not of similar length get the double dash, basically. That's how that would work. Angles opposite equal length sides are also of the same measure versus angles opposite non-equal length sides. A special subclass of an isosceles triangle would be an isosceles right triangle, and that would be an isosceles triangle with a right angle within it. So something like this. Okay, that's a very special style of triangle where this angle and this angle are the same, so therefore this side length and this side length are the same. That's an isosceles right triangle. And you do actually deal with isosceles right triangles quite often in trigonometry. But now we get to the heavy hitter. This is where pretty much trigonometry starts, with right triangles. A triangle which contains an internal angle of 90 degrees is called a right triangle. There's really not a lot I could say about that other than that, well, there's a lot of right triangles, right? So here's a right triangle right here, and we denote the right angle with that little square right there saying that that is the right angle. The side opposite the right angle there is called a hypotenuse. And the other two are just called sides. Side, I should say, that's not plural, and this is a side as well. Again, these are massively important to understand for trigonometry. Now, most students would probably look at this and say, of course, that's a right triangle, whatever. And that's perfectly fine. I'm okay with that. And of course, when you have a right triangle, you can't escape the Pythagorean Theorem. So everybody, again, pretty much knows the Pythagorean Theorem, but we're going to prove it here. So if you have a triangle ABC that's a right triangle with a hypotenuse C and sides A and B, then a squared plus b squared is equal to c squared. That is truly the birthplace of trigonometry, because this little identity right there ends up being one of what we call the Pythagorean identities for trigonometry. But let's go ahead and just draw this out as a picture so that we can see what I'm talking about here. Right triangle with angles A, B, and C, and therefore side length C, side length opposite angle A is side little a, side length opposite angle B is side length little b, and what this theorem is saying is therefore a squared plus b squared is equal to c squared. Now there are over 300 proofs of this theorem, and even one of our old presidents, Woodrow Wilson, did a proof of the Pythagorean Theorem because he was a school teacher. So let's go ahead and actually do a proof, one of the more simpler proofs that you could do for this, but it's a beautiful, beautiful proof nonetheless. We're going to start with a square, just this nice beautiful square, and we're going to cut it up into equal splits along the edges. Now what I've done here is I've gone ahead and sliced this into segments where this side length right here is, or this length I guess right here, is of length A, and this length right here is of length B. Okay, and I did that throughout. So this is of length A, and this is here. Oops, sorry about that. And this right here is of length B, and so on and so forth around the edge. And when we're done with that, we're going to connect up these little pieces. I'll show you what that means when I'm done shading here. Just real quick shading throughout. All right, let's go ahead and connect up those pieces. I'll use blue lines for that. There we go. So we have these nice lines connected to each of those slices. Notice they create what we call right triangles, right? So this is a right triangle right here. There's a right triangle right here, another right triangle right there, and yet another right triangle right there. And also, since you know the interior of the angles of a triangle add up to 180 degrees, then you know that, for example, this angle right here and this angle right here have to sum to 90 degrees. The reason why is because that angle in black, the single one, the double angle right here in black is the same as this angle. They're all kind of the same angle. So the single slash and the double slash should add up to 90 degrees. Well, since these are the same angles, these right here should add up to 90 degrees. And therefore, this is a 90 degree angle right there because they're all supplementary. And that was something I didn't define earlier, but they are supplementary angles. So let me go ahead and just create these as right angles, and therefore you have this beautiful square in the center because they all share the same dimensions, the triangles A and B. This side length, we'll just call that C just for giggles. C, C, and C, and C. And now I know the dimensions that we're dealing with here. And let's go ahead and find out the area of this square. Well, off to the right hand side, I'll do it here. The area of the square, well, that should be pretty easy to find because the area of a square is just the square of its side length, right? So it'd be the side length of this square, which is A plus B, squared. So it's the side length being squared. I'll just go ahead and write that over here. It's A plus B squared. And we know what that comes out to. It's A squared plus 2AB plus B squared. Very, very simple, nice and easy stuff. But that is not the only way to compute the area of this big black square here. We could also sum up all the areas of these triangles plus the area of the inner square. So 4 triangles plus the inner square should be the area of the big square as well. So let's go ahead and say that as well. So the area, let me just write it over here, is also equal to the area of the blue square plus the area of all 4 right triangles. So let's go ahead and write that down. The area of the blue square is, well, it's a C by C square. So that's going to be C squared. So I'm going to say that equals C squared. And then the area of 4 triangles. Well, an area of a triangle is 1/2 its base times its height. So we have 4 of those triangles. So plus 4 of those triangles, each having an area of 1/2 its base, which we'll call B, and its height, which we'll call A. Let me go ahead and convince you of that. Let me just take one of these triangles right here. Let's just take this one right here. So its base is this distance here, which is B, and its height is this distance here, which is A. So there you go. 1/2 B times A is the area of that. And we have 4 of those areas all together. Simplifying this, this is going to be C squared plus 2AB. Well, let's see what we've arrived at. The area of the big square should be, according to our mathematics, A squared plus 2AB plus B squared. But simultaneously, it should also be C squared plus 2AB. Thus, those 2 highlighted values, those 2 highlighted expressions, should be equivalent. Thus, a squared plus 2ab plus b squared, upper area there, should equal c squared plus 2ab. Notice you can subtract 2ab from both sides, and this implies a squared plus b squared must equal c squared. That is the proof of the Pythagorean theorem. Quod erat demonstratum. So it has been demonstrated. That is very common, I think, proof of the Pythagorean theorem. If it's not common, it should be, because it's a really nice proof. So let's go ahead and use it. The Pythagorean theorem, that is, not the proof. So let's solve this for x. It says solve for x, and they're given a right triangle. We happen to know in a right triangle, the sum of the squares of the sides should equal the square of the hypotenuse. That is x squared, this guy, plus 4 squared, this guy, should equal the quantity 2x minus 1 being squared. This guy. That's the hypotenuse. So notice how you can make an algebra problem out of a geometric shape using the Pythagorean theorem. Multiplying all this stuff out, just using our old school algebra skills, right? X squared plus 16 is equal to 4x squared minus 2x, which is 4x plus 1. And now I'll move everything over to the right hand side. So 3x squared minus 4x minus 15. And that should factor. This implies, I should say, 0. I should always do my implication signs. I kind of give up on them after a while, but this should factor. Let's see. I need two numbers that multiply to 15. Let's try 5 and 3. 3 times 3 is 9. 5. Yep, that'll work out. So I'm going to go ahead, put the 3 there, the 5 there. One of them has to be negative. And let's see which one that's going to be. Oops, nope, that won't work out, because if you just back off on that a little bit, you'll see. Again, one of them has to be negative. Well, if you tried to force one, let's say we force this one to be negative, this one to be positive. While we get the negative 15, we get negative 9 plus 5. No, yeah, actually that does work. I thought it wouldn't, but it actually does. So that's perfect. So we have two choices for x. Remember, x is a length in this right triangle. So you should always do logic checks as you go through a problem. Make sure that logically things make sense. So here we start solving. We find out that the product of two objects becomes 0. So either the first object becomes 0 or the second object will become 0. Well, the first object would require x to be negative 5/3 to become 0. Second object requires x to be 3. A negative number is not going to fly here. So we throw out the extraneous solution, negative 5/3, and keep the solution 3. We could double check that, by the way. That's a 3, 4, 5. That is the Pythagorean triple, actually. So that is perfectly fine. I should mention that again. That is a 3, 4, 5. In other words, if x were equal to 3, the side length here is 4, and plugging in x equals 3 to this expression, you'll get 5. 3, 4, 5 is what we call a Pythagorean triple. There are a whole bunch of Pythagorean triples that you kind of play with when you're working in trigonometry. 3, 4, 5 being one of the most popular because they're smaller numbers. All right, moving forward and just continuing this review of prerequisite material for trigonometry. Before we hit our right triangle trig, let's talk about complementary and supplementary angles. I mentioned the words during that proof of the Pythagorean theorem, supplementary angle. That is a prereq for the course, but still it's good to review it. Two angles, the sum of the measures of which are 90 degrees or is 90 degrees, are called complementary angles. So that is, if you have two angles, alpha and beta, and if they add up to be 90 degrees, they're called complementary. If you have two angles that add, whose sum is 180 degrees, we say that the angles are supplementary. So if you had two other angles, theta and phi, and they added up to 180 degrees, they would be supplementary. Now here's an odd piece that some students will ask, and it's stumped me, and I've seen different answers throughout the years. Students will ask, well, could, for example, alpha be negative 91 could alpha be 91 and beta be a negative 1 degrees? Would they be considered to be complementary angles? Now, mathematically, it seems like that sum should be 90 degrees, and it is, but we reserve the definition for two positive, non-negative angles, I should say. Two non-negative angles, the sum of measures of which is 90 degrees, are called complementary angles. Same thing for supplementary. It's not really going to get in the way of doing trigonometry if your instructor defines them differently. It's just that that's the definition that most people would agree upon, that you're dealing with positive angles. Mainly because you deal with complementary and supplementary in geometry, and the idea of negative measure for an angle is a bit weird. So let's go ahead and use those definitions, or at least one of them. So find the angle B. Let me go ahead and showcase what we're looking for. We're looking for this angle right here, the angle B. If alpha plus beta is 75 degrees and angle A is 50 degrees. So we're handed angle A to be 50 degrees. So I'll call this 50 degrees. The reason why I follow this, or this example follows the definition of complementary and supplementary, is because really you can use that language within this problem. For example, angle A, angle alpha, angle beta, and angle B are supplementary angles. They add to 180 degrees because they're the interior measures of a triangle. Okay, so that's why. So that kind of gives us a relationship here. Although, to be honest with you, the definition forces us to only deal with complementary or supplementary angles if there are two angles in question. So that is kind of a pain, right? But I can find beta at least because I know that angle B and angle beta are complementary. They should add to 90 because 90 degrees is already taken in the triangle right here. So I could say angle B plus angle beta should equal 90 degrees. Just like I can say angle A plus angle alpha should equal to 90 degrees. Well, if you look at that, they gave us what angle A is, so I can find alpha. So angle A, they told us is 50 degrees, plus alpha is 90 degrees. So therefore, alpha itself would be 40 degrees. So I can actually write that in here. That's 40 degrees. Now, also note that this angle right here is a right angle, which implies that this was a right triangle right here. That's why I knew that that was a 40-degree angle. And I spent a few moments here because I didn't read the rest of my instructions here. Alpha plus beta is 75 degrees. They have to give you that little piece of information because if they don't, you're kind of stuck, which I was just for a moment there where I was looking at this going, wait, how am I supposed to find beta? Because I don't have any other information. I do. I just didn't read it. So alpha plus beta being 75 degrees means that beta is 75 minus 40 degrees. I'll write it with 3 stripes there. So 75 minus 40 is 35 degrees. And now I can easily find angle B because angle B will be 90 degrees minus angle beta. That's from this equation right here. And that'll be 90 degrees minus 35 degrees. Oops, that's supposed to be a minus, not an equals. And what is that, 55 degrees? All right, so 55 degrees is what angle B is. There you go. So there is a good use of kind of the angle mathematics here. And again, don't be like me. You should read fully through the instructions. I just kind of dove into it without reading very carefully what the given information was. And that cost me a little bit of time. Okay, so that kind of finishes it for this video. So again, this video was just dedicated to getting us back into the mindset of dealing with triangles, dealing with angles, and all that fun stuff. And I should also just take a moment and say, well, what if I wanted to convert these angles into radians, right? Remember, 55 degrees is the same thing as 55 times 1 degree. And we happen to know that 360 degrees is the same thing as 2 pi. So if I divide both sides by 360, I'll know that 1 degree is 2 pi over 360, which is pi over 180 radians. And so I can trade that out. The only reason why I'm doing this is just so that you keep your eye on the prize. Keep your eye on the fact that we will be using radians quite a bit in trigonometry. And 5 goes into 180 about 36 times, so that'll be 11 pi over 36 radians. So not that I was asking, but still, it is nice to be able to do something like that every once in a while to remind you that we're going to be working in radians quite a bit. All right, that finishes it for this video. I'll see you in the next one.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry. Don't